Good morning, students. Today we are going to study about the ionic structure. In earlier two videos, we have studied about the formation of ionic bond and the formation of ionic compounds. In ionic solids, both oppositely charged ions are bonded together with a strong electrostatic force of attraction. This electrostatic force of attraction will be maximum when a cation is surrounded by the maximum number of anions or vice versa. How many anions are going to surround a cation will be the coordination number of that cation. Similarly, how many cations will surround an anion will be the coordination number of that anion. For example, in sodium chloride molecule, a sodium ion is surrounded by 6 chloride ions, hence the coordination number of sodium ion is 6. Similarly, a chloride ion is surrounded by 6 sodium ions, thus the coordination number of chloride ion is also 6. Another example, calcium fluoride. In calcium fluoride molecule, a calcium ion is surrounded by 8 fluoride ions and a fluoride ion is surrounded by 4 calcium ion. Thus, the coordination number of calcium ion is 8 and for fluoride ion it is 4. Radius ratio. It is the ratio of radius of cation to the radius of the anion. It is represented by writing R. So, radius ratio can be written as R is equal to radius of the cation upon radius of the anion. The formation of ionic crystal is highly affected by radius ratio. On the basis of coordination number, the formation of ionic crystal is determined. The most stable structure is that which have minimum energy, and in a crystal, if the surrounding oppositely charged ions are arranged in such a way that they are very close to each other and minimum space is left. Thus, a closed pack system arises which is most stable. We can have two types of possibilities. One, keeping the size of the cation same and changing the size of the anion. We have following three structure. Second one is keeping the size of the anion same and changing the size of the cation. We have following three structures. On looking to the structures, the center one, that is the structure B, both the anions and the cations are close to each other and there is no space left in between. Thus, this is the most stable structure and it enables cation to determine its coordination number or vice versa. In the structure C, in the first case, when the size of the cation is same, the coordination number decreases. And in the second case, where we have the size of the anion same, the coordination number increases. Thus, from the radius ratio, the coordination number is determined, and from coordination number, a structure of the crystal letters is determined. This is the table showing the radius ratio, coordination number, and shape. For the radius ratio from 0.15 or less, the coordination number is 2. Shape is linear, no crystal is formed. Example, HF2 minus. For the radius ratio from 0.15 to 0.225, the radius ratio is from 0.15 to 0.225. The coordination number is 3. Example is polymer metaborate Shape is trigonal. Example V2O3. For the radius ratio 0.225 to 0.414, coordination number is 4. Shape is tetrahedral. Example is zinc sulfide. Here both zinc ion and the sulfide ion are having coordination number 4. For the radius ratio 0.414 to 0.732, the coordination number is 6. Shape is octahedral. Example sodium chloride. Both sodium ion and the chloride ion is having coordination number 6. For the radius ratio 0.73 or 2 or above, the coordination number is 8. Shape is cubic. Example is cesium chloride. Both cesium ion and the chloride ion are having coordination number 8. Another example, calcium fluoride. Here the calcium ion is having the coordination number 8 and the fluoride ion is having coordination number 4. Limitation of the radius ratio. With the help of radius ratio, we have the information about the structure and geometry of ionic solids. But this is not always correct because due to the following points. First one, ionic radii. For calculating the correct radius ratio, we should know exact ionic radii, which is not possible. With the help of X-ray crystallographic studies, we calculate the exact internuclear distance but not the ionic radii. Behavior of the ions. In crystal letters, it is assumed that during packing, ions are non-compressible solid having a spherical shape. But at the time of packing, ions are fitted in holes, and if holes are very small, then ions are tightly fitted. Thus, the deformation of crystal letters arises. Third one is the arrangement of the ion. In ionic crystal lattice, a cation and the anion are arranged in such a way that they touches each other, but it is not always there. If the size of the hole is small, then it will move here and there. But if the size of the hole is large, then it will be fitted inside. Fourth one is nature of bonding. Compound should be 100% ionic if it follows the radius ratio rule, which is not possible. As in the ionic bond, somewhat of covalent character is also seen in some of the crystals, which should have cesium chloride type of a structure, but due to the covalent character in those crystals, they have sodium chloride type of a structure. Hence, from the radius ratio rule, we can have only rough idea of a structure in geometry of ionic compound. In study the calculation of the radius ratio.